Garrod and Dan Cervelli are software engineers at Palantir Technologies, where John is the lead for the Palantir Government Data Server team, and Dan is a senior member of the User Experience team. They were part of the team CDOG, which built the first prototype of Palantir's low-latency big data analysis system named Project Horizon. Please welcome John Garrod and Dan Cervelli.
How about now? Cool. All right. Hang on a second. All right, so giving credit where credit is due, let me explain everybody whose name on the slide. So Dan and I were half of the four-person team that made the initial prototype of Palantir Horizon, and actually all the code that you're going to see running today. The other half, Alan Chang and John Carino, are actually both UIUC alums, so thanks for producing them. And Brian Lee has done a lot of work after the initial prototyping. So Dan Cervelli here is really all about user experience. He works on our front end. He's really good at making things easy to use. So why is this important? Well, all of this crowd, all of us, we've grown up with computers. We really know how to use things. There are a whole bunch of people out there. If you want to put a face on this, this is your parents' generation, our parents' generation, of folks that are less familiar with things, so making software that they can really use is really meaningful. And particularly in our space, they're usually subject matter experts, national security types, where the things that they do really matter, so making software that they can use is really important. So that's what Dan does, and now, surprisingly enough, this is from CNN on Monday. He has the best job in America. You can't make this stuff up. Yeah. Also, you're old now. Sorry, Dan. So that's Dan. All the front end stuff. I deal with all of the back-end infrastructure. Various things like, well, the backend for Horizon, the backend for Nexus peering, which is how we enable cross-agency data sharing, sort of important in the government these days, search, database stuff, so on and so forth. So essentially, if users can't see it, I've worked on it. So that's me. All right, but okay, so we're here to talk about Horizon, not what we've done or what CNN thinks of us. So a little bit of introduction. First off, for the room, how many people have heard of Palantir before? Like before just like the name on the intro thing? Yeah, okay, some. Cool. Anybody familiar with what we do? Maybe a few? Cool. All right. So we're gonna run through an introduction of where we're coming from, how we're attacking this. The next thing is we really love this stuff. We can talk about this for hours. You could drag us out of here kicking and screaming. So I'm going to try and give you a brief overview of everything, and then we can go deep on whatever you're most interested in question time. So with that, you know, if you see something interesting for questions, I'm actually okay if you jump in, or you can write it down and we'll talk about it at the end. So this introduction of what is Palantir, where are we coming from, let me start with the mission statement. So this probably looks pretty familiar. Organize the world's information and make it universally accessible and useful. Palantir is too small to have a mission statement, but this is Google's. You know, small company stuff, big company stuff, in any case. So this is Google's. So this is kind of where we're at. And you're like, oh, holy crap, what are you doing competing with Google? Well, actually, we're not. So what is Google focused on? Public information, everything on the web, and making it accessible, but maybe not useful. So what do I mean by that? Well, really, we're doing the other half of that. So this is private information. This is making it useful, not just data. So we make software that takes data and makes it useful to people. Human-driven analysis. So you can kind of think of software and data and people making up the spectrum, where at the one end is data. the bits and bytes, and at the other end is the human. And there's a long way in between these things, and software falls somewhere in between them. If this is like grep and regular expressions, it's pretty close to the data. And you could argue that like SQL is like a little bit higher level language. Excel and graphing things, okay. We're building software to be right over here, to be really close to the human so that you don't have to be a whiz kid to use it, but you can still do really, really powerful things with it. That's really hard. There are a lot of challenges to that, and making that experience and that ease of use are really what Dan really excels at. So now that's useful versus accessible. So what do I mean by private data? So there's all sorts of stuff that I'm really happy is not public information. Things that are classified. I'm glad that's not public. Intelligence, defense, law enforcement stuff. Medical records. That's privacy is a good thing. All of our spending within the government, we actually do a lot of work finding fraud within Medicare spending and within other areas of the government. And then this sort of a new thing is network security data, and this is particularly interesting because there's just so much more of it than anything else. All right, so this private data matters, and I'm not just saying that. This is Vice President Biden, and that's Palantir behind him. What we do really affects national policy in the world, and Dan and I really like working on hard problems that are perhaps more important than Farmville. Perhaps. All right, so that's what Palantir is all about. What is Horizon all about? So we're a small company. We don't have a research department. We don't have any departments. We attack whatever needs to be attacked next. And building Project Horizon was a prototype to understand a bit more about big-scale data analysis, because this really changes things both from a back-end, bits and bytes, how do you get the most out of the hardware perspective, but also most importantly from the usability perspective. Visualizations that work at thousands of things just break down at millions or billions of things because people can't understand what's going on. So that's really huge. All right, so Horizon is our prototype to learn a bit more about this. What do we want it to be able to do? Well, first it needs to be able to aggregate across lots of data. If you have a billion things, I'm not going to show each one of them. I have to aggregate in some way. So this is timelines of like, when did things probe our network, heat maps of where is fraud going on, things like this. The next is, so you can attack the first problems with some numerical analysis. But the second is a really interesting thing that a lot of people overlook when they think data analysis is what we call graph-centric stuff. So a graph in the like network of node and edge sense. Things like, I have all of these campaign contributions. Now show me which political action committees did they go to. That's an edge traversal in a graph. That's not something that yields itself to just a numerical analysis. I want to see which PACs these campaign contributions came to, who did they donate to, find any nefarious connections, things like that. That's something that Palantir is really good at and that nothing else really exists for. It needs to be really fast. If we, this will make a lot more sense when you see the demo a little bit later, but like, I have a question in my mind, I click, I get the answer, and in a matter of seconds. This is very different from like, I start some job and it runs overnight, or I start some job and it returns in 10 minutes. It's just a night and day difference. And finally, because data sets are always growing, making it linearly scalable. So you just throw more hardware at it, twice as much data, twice as much hardware, twice as fast, things like this. So that's our goal with Horizon. So let's, that's all the background we need. Let's jump into a demo. Now, Dan's going to pull this up here. Cool. All right, so let's start off with the firewall data. This is not a big data set. This would run happily on this laptop, but it's useful to give you an idea of what we're talking about when we talk about like network security stuff, and also to just give you an introduction to the UI that's going on here. So just to get an overview of these things, let's look at when these came in over time. So this is 10 million network events and gathered over about 24 hours. So this is a fairly verbose logging mechanism that's giving us this data. And this is real data, so it's got its natural variance going on.
So one important thing to mention, is this on?
Yeah, just pull it up closer to you.
One important thing to mention is that the original design was for 2 monitors. So I'll just be flipping back and forth between what would be a left and a right monitor. So bear with us on that.
Hopefully it's not too jarring. So, okay, so this is real data. Let's go make the graph of the zones. So from zone and to zone. So for those of you who don't administer corporate networks, okay, everybody, firewall zones are a common thing that people do to make it easier to run a network and set up rules about what should go on. So essentially, instead of specifying for each IP address, this is what's allowed and this is what is not allowed, they set up zones, and then they have some mapping for IP addresses into the zones. So what did we just do? We just took 10 million events, and as fast as Dan could click, we visualized where network traffic is flowing between different zones. So this is really useful for an admin to get really quick idea of what's going on their network. You know, writing a script, going through the logs, something that I think a lot of you could do, but you can also expect that there are a lot of people in the world that couldn't do that. So having a user interface to make that possible is really valuable. Now, we anonymize this. I won't tell you what subnet 1 really is, but it's good that it doesn't talk to the outside world. And we can also see things like about half the traffic is flowing between inside and outside, so about 5.5 million of these 10 million connections. All right, so this is network data. We were talking about network security. So let's say, you know, security is like an onion, and you've got layers and layers and layers. And so you've got this firewall, you've got some antivirus. But what's your last layer? Well, at some point you expect somebody's going to get in, and you want to notice when they did. So let's say we're worried about people getting in and pulling some sensitive data off of our network. So let's look at, this is just a visualization of the sizes, the amounts of data transferred by each connection. We're going to look at the smallest set of these guys, and this is sort of a nice little end around. What we really want to do is look at everything but the smallest. And so I'm sure all of you are pretty familiar with set theory and union and subtraction and things like this, but giving a way that regular users can do something like that, just dragging around these subsets, these pieces of the data, and making that easier to understand. Okay, so we're looking at all but the smallest. Now let's say we want to see which computers this traffic is going between. And the theory behind this is essentially, well, if someone penetrates our network and they go get onto some really, really sensitive box and it's got some really sensitive data on it, and now they want to get it off of our network. Well, we would have noticed if they just like directly connected to the outside world on that zone diagram, because we would have seen the subnet 1 go connect to outside. But if they're clever, they'll pass it first from one computer to another, and so on and so forth, and then slightly less sensitive computers over time, and then pull it off at the end. So we're looking for like these long chains of traffic passing around. I'll tell you that in this instance, nothing was stolen off of our network. But this is the kind of thing that, you know, this is buried in people's log data somewhere, but giving them an ability to actually look at it makes it usable. Yeah.
Question. You're looking at trace routes where the background where it hops from.
Mm-hmm.
If you're looking at logs, usually they don't represent all the hops that are actually taken. How are you getting that information?
Yeah. Sure. Let me. The question is essentially, how do we get all this data about what hops the attacker took? And the important thing here is this isn't off our network data, so we're not seeing like they bounced it off of a satellite and they bounced it off of Norway, that kind of stuff. This is data from like our routers saying this computer on our network talked to this computer on our network. Yeah. Pardon? So the premise here is not about tracing the origin of the external attack. The premise here is if something is going on our network, we want to understand what it is. And right now it's just lost in the sea of data. So you can collect whatever data you want about your own network, but if you can actually visualize where things are actually going on your own network, you can see I've got this sensitive machine. It's sending a lot of stuff down and out. Yeah. Cool. All right, so that's an introduction to network security data and to this visualization. Now let's get to big data. So this is data collected from the Home Mortgage Disclosure Act. This is 7 years worth of every mortgage and every mortgage application in the country. This is about $250 million. This is some sizable big data. Let's just get a feel for what's going on here, and we're going to heat map what all of these mortgages are, where they occur within the U.S. Now, cool. This takes a couple seconds to load up the imagery and all that good stuff. This is the first data. So the other data set would happily run on this laptop. This data set is running with some real backend hardware behind it, but only about $5,000 worth of server hardware. So this is like a very reasonable amount of hardware for making calculations like this. And so, okay, so we did this heat map. This is really what you should expect it to be. This is just unfiltered mortgages, so it looks a lot like population density. We've got the West Coast, East Coast, Chicago, Detroit. Okay, cool. Why are we looking at this data set? Well, we're looking for any kind of predatory lending that went on during the subprime crisis. This is something that people reported on in newspapers, but it's unclear how much was actually found. And because there's so much data there, even though the federal government requires that it be reported, I may have my doubts about how much they can actually look through it and find stuff. So for everyone in the room who hasn't bought a house, let me just explain a few things about mortgages. So spread is the difference in interest between what the mortgage costs and the prime rate. So this is essentially a time-independent measure of how expensive a mortgage is, because the prime rate goes up and down and the mortgage rates go up and down. But if you're paying 1% over prime, that's a measure that is a good measure of how expensive it was over time. Okay, so we have this visualization of how much spread people are paying, and this is real data. So this is some folks are actually paying 100% mortgage. I hope this is like misentered data for their sake. This is a log scale, so it's only about 100 people, a few hundred people paying these extreme interest rates. Now, we're going to drill down on the spread between 3 and 30%, and let me explain why there's nobody between 0 and 3. The Home Mortgage Disclosure Act dataset exists because of federal requirements on reporting of data. Banks don't have to report any spread less than 3%, so they always report it as 0%. So that's this emptiness between 0 and 3. So we drilled down on sort of like from subprime to like the last area where there was any real number of mortgages at that interest rate. Now, looking again at that 3 to 30%, this is a really interesting curve. Like you never see a curve like this in nature. What's going on? Well, 5% is actually the reporting requirement that turns on reporting of subprime mortgages for second mortgages. So all the second mortgages come in at 5% or weren't reported if they were 4.5 or whatever. Cool. The next thing, and this is a little bit hard to see from the back, but there's like a really quick drop off here at 8%. Like a lot of people are getting these mortgages in at like just under 8% spread. Why is this? It turns out federal government increased scrutiny of potentially predatory loans at this like super subprime 8% and higher spread. Okay, well if this is the federal definition of potentially predatory stuff that they should take a closer look at, let's look at it. So we're going to drill down on this. And now let's, because we're worried about people targeting the little guy, let's go look at income. And we're just going to drill down on the leftmost bin. We're going to go and find everybody with up to the median income. So this is going to be, we're going to drop the zeros, considering them bad data, but up to $40,000. Okay, so we drilled on these guys, and let's look at amount. yeah, this is a real data set. I don't know who makes 40 grand a year and has a $2 million mortgage, but they're in the data set. Good luck to them. Let's drill down on amounts up to 100,000. And so this isn't actually the home value. This is the mortgage portion of the home value. So we're going up through about $106,000. So this is a real home mortgage for most of the country. So we kind of dove through a bunch of things here. Let me review how we got here. So we started at all of these mortgages. We went to the subprime ones, so 3 through 30% spread. Super subprime, 8% and higher. Income up to 100 grand, and then income, 1,000 through 40,000, and then amounts up to $100,000 mortgage. Okay, cool. This is our hypothesis of like potentially interesting, potentially predatory loans. Let's see where these are happening. And this is like a totally different picture from what we saw before. All of the heat is in Detroit. Okay, so this is the prior picture. This is just population density. Okay, let's compare that. We've got all this heat in Detroit, a little bit in Ohio, a little bit in St. Louis. Something interesting is happening in Detroit. So let's drill down on that. Other lake.
Up in California.
Zoom out a little bit. Yeah.
There we go.
Cool. Cool. All right. So we've got these Detroit mortgages, and let's look at where these are going. Now, note about this data set. We cannot zoom in on your block and see what you're paying on your mortgage or what your parents are paying on their mortgage. But it's anonymized just to the census tract level, and in an urban area, the census tract is just a couple of blocks. So we can zoom in on urban Detroit here and see like exactly who's getting screwed with their really high spread mortgages. Now, this is extremely hard to read if you're not like standing this close to the screen, but this horizontal dividing line is 8 Mile Road. I don't know if any of you guys listen to Eminem, but this is not exactly a nice section of town. Okay, so we think we've found. We've just gone through 250 million mortgages. We've found interesting stuff happening. We see where it's happening. We know something about who it's happening to. Who's doing it? So we're just going to look at all the banks involved in this and sum up how many mortgages they're doing. And Countrywide takes the cake. We present this data on our website, and we blank this out. We think this is so damning to Countrywide. We've reported it to the appropriate authorities, but yeah. Anyhow, Countrywide. All right, so Countrywide is in the news. Like, if you came to this presentation and you're like, all I learned is that Countrywide engaged in subprime lending, like, I haven't really told you anything. So let me demonstrate some more value. So we're going to take these Countrywide mortgages. Now, Countrywide is a huge bank. Maybe they just dominate these Detroit high spread mortgages because they do high spread mortgages everywhere. So let's look at Countrywide's subprime loans, 3% and higher in the whole country. So we took this filter of just this Countrywide bank and applied it on the 3% and higher spread. And let's look at where these guys happen. So this is very much like our original picture. Chicago and LA, very little in Detroit. Let's take this Countrywide filter and apply it to these super subprime mortgages, and then see where they happen. And it's all Detroit. So we spent like 5 minutes right now demoing this. It only took us about an hour to find this when we were just like, okay, here's a data set, let's find a story. If you're a federal regulator and you have 250 million forms to look through and find something bad going on, and you're underfunded and time is limited and you don't have that many people and all that stuff, in a matter of minutes you just found not only what bank should you look into, but which branch office should you look into. We think this is really cool. So let's go back to those Detroit mortgages because there's even more story there. So we've drilled down to a small enough level of scale. Yeah, actually, I'll take a question first.
You said this was running on like $5,000 server
Yeah.
equipment. Given any arbitrary data set, about how long would it take to set up?
This is thanks for not being an audience plant. So the question was essentially, how long would this take to set up? We're a small company. We share hardware. We shared the hardware that this demo instance was on, and we had it all set up yesterday. Somebody took it down last night. We discovered this about 2 hours ago. And we had it all back in. So, yeah.
The original data set has 350 million, and we calculated that at 130 we could have 250 million, so that's what we went with. So.
Yeah. 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 Mm-hmm. Right. So the question is essentially around, it's really valuable to know what data is in the data set. It's really valuable to decide what goes in, and what gets visualized. So what goes in is like mandated by law and by Congress, and like takes years to change. I think the act that decides what gets collected was from 1996. Now, there's a like technical question of which fields do we want to pull into Palantir, so on and so forth. This was like 20 lines of boilerplate to be like, okay, I want these fields. This one is like an enum for which state things are. This one's a double for what income is, things like that. This is a prototype, so we weren't like productizing a very nice visual importer, but it was.
So in the
Will wrote an importer. Will is a BD guy. He's not a developer, and he wrote that in like 2 hours.
Something like that.
Yeah.
But I mean, it's important to note that this is a prototype, and it has subsequently been productized. And the main Palantir government product has a complete visual system for doing data import, and this now powers a large part of that platform. So you can leverage the import capabilities that we've already done for our main platform here.
Cool. Does that answer your question? Cool. Yeah, there's no specific UI for importing into Horizon, but it's like really easy code. Yeah. The question is essentially around where is this data coming from? Is it a data mart, data warehousing kind of thing? And yes, yeah, exactly, pulling it out of there. Actually, to the question about how long does it take to pull in every instance we've run at a customer site, it has been how slow is the data warehouse that we're pulling it out of, not how fast can we ingest it. Yeah. Yeah, is the data set assumed to be static or live? Actually, by recording this path of analysis, and we haven't done it in the prototype version, but we did it in the productized version, all of these filters and drill downs can be reapplied so that the root of the data set can change, and it just flows all the way through, and you can see, just hit refresh, and it pulls up whatever it's got.
You can sort of see that now where I've been dragging and reapplying formulas. Actually, as we continue through the next part of the demo, you can sort of see that in action a little bit.
Yeah, yeah. So let's dig into a bit more of specifically what's going on with those Detroit mortgages. And now we've drilled down from 250 million things, to a few thousand. So this is a scatter plot of those mortgages. This is finally possible to do a visualization like this where we have a data point for each mortgage because we've gotten down to a small enough scale. So the y-axis is the amount of the mortgage, and the x-axis is the spread. So essentially, the higher up, the more expensive or the bigger the mortgage, and the further to the right, the more expensive or the more you're getting screwed, pardon my language, by the bank. So the important thing here to note is just how high these interest rates are. There's sort of a drop-off at 20%, but there are two forks of these mortgages that charge more than 20% interest. This one fork is like a couple $1,000 mortgages, and like I'm just speculating here at how these things were advertised, but this is essentially like credit card sized amounts of debt at worse than credit cards are allowed to charge levels of interest. Just really taking advantage of people. And the other is for the Detroit area, really like a we're going to take your home away kind of a mortgage, because at 25% interest, this is, or 25% spread, so probably like 30% interest. This is compounded, doubling every 2.5 years. This is just like, this is really expensive and sad to see. So let's drill down on each of these and see what's going on. So we'll drill down on these small guys and see which banks are behind them. Yeah. So we're gonna see here. Do the same grouping histogram that we did to show Countrywide for all the Detroit mortgages. And we've only got one bank here. So like there's one bank that specializes in like really small, incredibly high interest mortgages in Detroit. These are fun guys. Okay. Let's go look at this other fork of these mortgages. And we're going to see which banks are behind those. And it's one bank that kind of specializes in that.
And his friend.
Yeah, and that other bank that we saw before. These are fun, interesting people. MLA specifically, I remember we Googled them to just see what their website was, and I think they've fixed it now, but it used to be like an under construction with an animated GIF guy like going. And
they're back. They're
back. All right. At some point, it was like taken down. I hope they go out of business. Yes. All right. Okay. So what's the interesting part of this? So we found two small banks involved in interesting things here. Let's take this filter of these like pretty high interest mortgages and go apply it back to the whole data set. Now this is going to take a couple of seconds to run because we're back to considering this whole 250 million mortgages. But what it's going to pop up is, so I said this is 250 million mortgages and it found 407. So this is almost literally 1 in a million. Let's see. So this is now on a national basis who are doing mortgages of the same type. And it's our old friend MLA.
So basically they're the only ones doing this.
Yeah. So in the whole country, they're essentially the only ones doing this. Yeah. So if you're a federal regulator, it just took you not that long to look at, which branch office of Countrywide, and then these MLA and American General Finance stuff. This is really powerful for like, I have a giant haystack of data. Let me find the needles. Let me find them in a specific example like Detroit, and then see if that teaches me anything about the whole country.
And also, it's about finding needles in haystacks, but once you finding those needles, reapplying that to the whole haystack again and going a different way, which is pretty cool. All right.
Cool. Any other questions about this data set? We can, yeah. Yeah.
As you drill down in large data sets, small subsets have data reliability problems, especially when you're looking at outliers. How do you identify those? How do you say this is bad data and throw it out?
Sure. So the question is essentially around outliers. And how do we identify and discard outliers? This is actually a really interesting point. All of our government customers are essentially looking for outliers. In law enforcement and counterterrorism, you're not looking for the 99% of the population that's law-abiding. You're looking for the 1% that is the outlier. In all of this fraud detection stuff, you're not looking for the 99% that are doing the right thing. You're looking for the 1% that are doing something weird. So you very much are looking for outliers. Now, there may be data bugs. There are mortgages in this data set that are negative. And that, like, at the end of the line, like, somebody entered the data and they can mistype it. So essentially all of our government customers are looking into this stuff, and all of our anti-fraud customers. In the commercial space, anti-fraud is looking for outliers, but a lot of people are also looking for what is the general trend. How are things going there? So it's a very different kind of analysis.
Another point, a couple of points there, is that you can sort of munge the data a little bit before you take it in, maybe take medians or something. Well, actually, medians are tough, but do some statistical analysis to find out if you want to flag certain things as outliers, and then you can sort of use the horizon to look at what it is about outliers that makes them outliers, right? Look at the other fields to see if there's something causal, and then using the set algebra, you can subtract out things that you think are not worthy in the main analysis or something like that. Does that make sense?
This is very much made for like rapid iteration of analyzing things, and I guess a very important point about outliers is people can identify them. Automated systems are like a little uncertain about it, and so making something where it's very easy for a person to look at it and decide, is this a problem or like obviously doesn't matter, that produces a lot of value. Yeah. Aha. So this is essentially leading into the next section. How is the data stored? I'll answer that in turn. Yeah. Yes. Next section. All right. Any other questions about HMDA? Home mortgage disclosure? Okay, cool. Let's roll on into the next section. All right. So there are a lot of things that we have to do. Essentially, if anything in your system is slow, your whole system is slow. So we have to attack each of them individually. First off, data is never duplicated. We go to great pains to achieve this. We did a back-of-the-envelope calculation, given a reasonable number of analysts and a reasonable size data set, and they click and analyze things at a certain rate. How much data do they end up duplicating if we did duplicate stuff? And they would run out of disk space like every day. So avoiding duplicating data, good. All right. Next is we actually use this in memory, and this goes as part of the perf stuff. And this goes hand in hand with how we avoid duplicating data. So like avoiding duplicating data lets you be smaller, which lets you be in memory. Being in memory lets you avoid duplicating data in other ways that I'll explain, which lets you do everything good. It's very compact. We're writing for, there's some question about general case data sets, anybody else's data. We're in Java. Number one, Java has a lot of per object overhead that we have to deal with and get rid of. Number two, we're not writing a like analyze mortgages piece of software. We're writing an analyze any kind of data piece of software. So there's a lot of stuff that we have to do to be able to deal with any kind of data. So we end up being column oriented, and this lets us get a few things. So back to our network traffic data. If we had IPs and ports, IPs should be 4 bytes, ports should be 2 bytes, and you should not have to spend any more space than that. And so how do we achieve this? Well, in Java, parallel native arrays. Very efficient. You get to amortize whatever the overhead cost of that array is, and your per object space is what you want it to be. This works for all kinds of fixed width types. Years, dates, locations, everything. So that works for fixed width types. What do we do for variable width types? Strings. So the string Java object has a lot of overhead to it. But the substring operation is really fast. So we just concat together all of the strings, so foo, bar, baz, and then store a fixed width record, which we've just said was really efficient, of where within our giant string that is and how long it is. So we end up having like 65,000 strings all concatenated together, and then very quickly perform a substring operation to look up where they are. Now in Java, string is implemented with an underlying char array, and substring produces a new string Java object, but it actually just is a view through to the underlying prior strings char array. You don't have to copy the chars. You don't have to, actually you might have to recompute the hash. It's very quick, and it doesn't duplicate data when you do that. Okay. Another thing, real data sets also have a lot of multiplicity. In the real world, people have more than one name because they've entered it multiple ways. They have more than one address, more than one phone number, things like this. So having a system like this so that we can deal with multiple records is really valuable. Cool. So the next thing is, by being a column store, we make things really compressible. All of the values within a column are pretty similar. If you think of the bank names in our data set, they compress pretty well with each other. Now, we're reading these in a very tight inner loop of analysis, so we can't have a really expensive compression scheme. But we use dictionary compression and prefix-based compression, and this is really fast to decompress and really useful for us. So how does this work from a who calls whom and how does the data move throughout the cloud? This is essentially the client starts this operation, Dan clicking on something, that executes in parallel on a series of servers. This diagram was 4. This is running on 16 processes across 2 physical boxes for this demo. They execute in parallel on each of those boxes, summarize the results locally, return the summary of each box's results to the client, and then the client collects together and aggregates the results from each of those machines. Shared memory, shared disk are not the way to go anymore. This is a shared nothing architecture, and for the DB nerds in the house, that'll make sense. All right, so let's see. We go to great pains to avoid ever duplicating data. We also go to great pains to avoid ever sending it over the network. And for these 250 million mortgages, each ID is 8 bytes. So the ID set specifying all of these mortgages is about 2 gigs. Now, even if you're on gigabit networks, it's gigabit, not gigabyte. So if we had to send all of the IDs saying, hey, analyze these 250 million mortgages, this would be something on the order of 30 seconds just to send all of that data. As you saw, it's obviously a lot faster than that. So what are we doing? Well, we're taking all of those IDs and divvying them up between shards according to the same partition scheme that we use for divvying up the objects. This minimizes cross-shard and shard-to-client communication. Cool. So the next thing is the operations and the computations that you perform on this data have to deal with the fact that they can't access all of the data at once. So this has some interesting implications. For example, it's really easy to compute the mean in a sharded data structure. It's really hard to compute the median because the exact values on the shards can affect you. The views and formulas that we write on top of this have to be very careful to be efficient. And this affects not only the code that we write, but also the code that our customers write that plugs into our data store. So let me explain a little bit more about all of that code and all of that stuff. So to give a motivating example, let's say we want to make this visualization. We want to make this this chart. Okay, so how do we do that? So let's define a few terms. First off, a view is just our term for a computation on the data. It visits all the data in a particular subset and usually is looking at something of it. Now, formula. This is something that takes one or more subsets and perhaps some other arguments and produces a new subset. So maybe this is a filter for mortgages where income was under 100,000. Maybe this is a set subtraction between 2 sets of mortgages. And finally, a visualization. I want to be clear that visualization is distinct from view. A view is a computation on the data, and a visualization is something that uses the results of one or more views. So this view, we can actually dive into a lot of details on how do you implement these things, and I'll move as much of that as possible to question and answer. I don't want to bore the crowd, but essentially it's visit each object and reduce and aggregate, combine the results from views that ran on separate machines. What's really cool about this is Palantir has done all of the hard stuff, the hard multi-threading, the hard distributed system stuff, the hard dealing with different shards, and the clients who are writing on top of this only need to implement these 2 methods, and they don't have to worry about all of this other stuff. So how does this work? Well, the client sort of initiates this call to do these views. Each server runs it in parallel. They come up with their local results, they send that to the client, and then the client aggregates all this stuff together. So a visualization is typically the result of one or more views and is a graphical representation of that. So we happen to have used a lot of our own hand-rolled visualizations, but there are a lot of visualization frameworks out there that you could use as well. So you can sort of think of this as being two steps: a computation step where you do one or more views. For example, for that chart that we showed you, probably the first view would be figure out what are the bounds of my data, and the next one would be, okay, given the bounds, I know what buckets I care about, and I will now count how many values occur for each of these buckets. So that would be the compute step, and then the render step displays this, turns it into pixels that the user actually cares about, and shows it to them. We've got full API stuff here to talk about. Any questions if you guys want to go back to it. So that's a view, that's a formula. Now, typically the first question we get after we talk about this stuff is, hey, isn't this just like MapReduce? And it isn't. So we'll explain a few reasons why. First off, we read as little as possible. By being a column store, we only have to read the column that we deal with, and by dealing with only subsets of the data, we only have to touch the subset that we care about. MapReduce retraverses the whole data set. By being in memory, when we're reading just the parts of that subset that we care about, memory is random access, so we can access those individual records very quickly. If we were on disk, we would be dominated by the seek time to get to that record within the data set. As you saw, this is really fast. This is interactive. Like, as fast as Dan clicks, the result comes up. Hadoop, MapReduce, Google's own number for what the average time of a job is inside of Google is 10 minutes. We've been talking for, I don't know, half an hour now, 45 minutes. If we'd only been able to do 4 clicks, that would have been somewhat different, especially since some of those operations involve multiple views. So that would not have found everything that we wanted to find. We only have one copy of the data. MapReduce on drill down has to copy it. This is okay for Google because the people who are doing data analysis there are software engineerish types and know how to move things around. When can they avoid duplicating things? When can they delete things? This doesn't work if you're trying to make software for the older generation, for very simple users who aren't worried about the implementation and who aren't worried about the resources underneath. They just care about finding fraud or finding bad guys or whatever it is. So this random access is really valuable versus full sequential reads. Next, Google gets to quote some really cool numbers about how much data they crunch. This is running on $5,000 worth of hardware, not 5,000 machines. Working on big clusters of machines is great for Google because they have it. We're making software that our customers are running, and they don't have that many machines. So they need something that they can run with just the hardware that they have. And finally, this is a really interesting note that's sort of hard to understand from the outside is Google administers their own data centers, so they can control what goes on. And we have to do a certain amount of idiot proofing of everything. If the program crashes, it can't just page whoever wrote it and have them wake up in the middle of the night and fix it. If that's inside of a classified facility, that's just not an option. So it has to be much more self-contained. Cool. So that's a lot about how, where it's stored and how it's fast. Now, this has sort of been very back-end focused, so I've been talking, but Dan's going to talk about how we make this really accessible for average users, and that's a really important part of this.
Yeah, so let me just jump to the next slide. So, yeah, sure. How's that? How's this? Is that still? More? How's this? All right, cool. Okay, so the stuff that John's been talking about, I sort of think of it as the prerequisite to building really good software. I mean, without really good back-end technology, you can't even start to make a good front end. So I don't want you to take away that this guy thinks it's all on the front end. Well, I do, but no, I understand that all the back-end technology is super, super important, but it's not sufficient, right? I want to measure success in how effective are our users. And when I'm talking about users, again, it's the people who have subject matter expertise, who are not necessarily, people like you. All right, go ahead. So what are some of the constraints here? The visualizations have to be very general. They're not like specific infographics that you might see in New York Times or USA Today. they have to be able to handle any case and be useful in all these different use cases. Horizon is built around this notion of sets and subsets, which intrinsically is a little bit tricky for a lot of people. I mean, people with math backgrounds like us, it's no big deal. But I wanted to make sure that if we were going to expose the notion of sets, that it wasn't in some sort of scary way. It was just sort of these boxes of information, which are sets, and they're not so scary. And then I wanted really simple navigation of the whole sort of workspace, like the analysis I've done, the visualizations I've made, and go ahead, next slide. And which leads into being able to do comparative analysis between some of the different visualizations. So on the left there, I've got some heat maps of the countrywide mortgage distribution with the Detroit and the nationwide. And it was really trivial to just sort of pile up all the visualizations you make, and you get this ability sort of for free. Which, given that this was a prototype, we built it in just a couple of weeks. That was, it was the simplest thing to do, which is almost always the right thing to do, incidentally. We didn't show those graphs that are on the right there, but it's another way of looking at comparative analytics. It's mortgage distribution by race. We can do that in the Q&A if anyone wants. Go ahead. And another constraint was extensibility of these visualizations. So this was built by some of our beta guys who were basically trying to come up with a visualization that would mathematically look at a subset and say and tell interesting things about it. So what they've done, this is against the same data set, the 100 data set. It's given this particular subset, whatever it is, maybe mortgages in Detroit. If action equaled loan originated, I'm hovering over one of these lines here for a tooltip. It tells you something like, given that ethnicity is Hispanic, it's 0.73 times more likely that action equals loan originated in this subset. So this we call it the pocket histogram because it finds little pockets of interesting behavior. And they wrote it on their own, just using the view interface that we can talk about, and it's really pretty cool. All right, next. So the four of us, JG, me, the two UI UC guys, we had this idea, which was we want to be able to do interactive analysis on really big data. But it's having an idea and executing on it are two entirely different things. So we work full time, right? How can we get time to do this? So Google's answer is 20% time, right? Which is really pretty awesome. You get to spend 1/5 your time working on stuff that you think is just important or valuable or fun. But for us, we sort of shove all that 20% time into one block. Back then, it was called Hack Day. We call it Hack Week now. We cheated our asses off. We spent 2 weeks on it, and basically, our bosses knew we weren't really working on what we were supposed to be working on, but they sort of also knew that we were doing something that we thought was going to be really valuable and really cool, and they just let us do it. So this is, now that it's Hack Week, this has sort of been baked into the whole culture of the company, that anyone in the company can do this during this time. So that's how it was created. And it's sort of, it's like of all the perks of working at Palantir, I think this is the best one. It's like whatever, there's food and all this sort of Silicon Valley stuff that you get. But for me, having a company that sort of knows that innovation can't just be commanded and is willing to set aside weeks to make this happen organically is really cool. All right, so what's turned into Horizon, or what has Horizon turned into? So we shipped Palantir Government 3 a few months ago. It has what we call Object Explorer now, and it's the productized version of this. It looks pretty different. It does share a lot of the code, quite a huge amount of it, and it's also had some unexpected side effects of sort of reworking how a lot of the product is built. I mean, those are details we can get into in the Q&A. It is definitely currently in use in the field. Go ahead. So I'm going to close on this slide, which is Palantir builds platforms and applications for human-driven analysis. And I think this is sort of where we're going. I mean, I don't know if Ari talked about human-computer symbiosis, but if you haven't talked to him about it, you should. It's a very interesting topic that he speaks very well on. But the important point is that without a human, these massive amounts of data that people are collecting are just not going to be particularly useful. It takes the human with the right tools to be able to get meaningful conclusions out of big data. And with that, we'll go to Q&A.
So we have some Q&A fodder, or we'll just take questions until then. Yeah.
How long does it take someone to get proficient at using the application? So like when a user sits down for the first time to when they can actually do that analysis?
Okay, so that's a really good question. So what we're showing you right now is basically the prototype that we demoed plus a little bit of extra work that people wanted for other features. So not a lot of like end customers got to use this. A lot of our BD people actually still use this version a little bit. But the Object Explorer version is very easy to pick up. A lot of the complexities of this were hidden to get just that much more usability out of it. And I can't give you any hard numbers like in 10 minutes they can do it, but it's pretty intuitive. I think we had a conference last Tuesday, and there was a talk. Do we put those talks up? Will they be? So there will be a talk up, hopefully within the next week or two. I don't know when, by Eric Lynn and Brian Lee, showing this new version. They analyze a bunch of baseball statistics. It's very interesting, and it will give you a better idea of what the UI looks like now and how approachable it is.
This stuff is extremely approachable. You're welcome to come play with it afterwards.
Yeah, that's true.
I wouldn't want to sidetrack a couple hundred people onto it, but yeah, we love talking about this stuff, so come try it out. The whole product obviously has a lot more power to it, and we do one-day training. So this is, by the time you wedge it into the government workday, it's like really 4 hours, but yeah.
Yep.
A lot of people that we can't talk about.
Yeah.
Yeah.
There's some that we can, though, right?
There are plenty of things that we can't talk about. So, like, all of the people in intel, defense, law enforcement, we really can't talk about. You can read a Wall Street Journal article for their opinions about who we work with.
Their opinions.
Their opinions that we neither confirm nor deny. We publicly work with the RAP board, the recovery, essentially a group that finds fraud in the stimulus package. That's what Vice President Biden was demonstrating. Is that public? All right. Medicare and CDC fraud finding. Yeah, so very.
CDC is Center for Disease Control. That's outbreak mitigation.
Yeah. A lot of the things that make the world either a safer place or make sure that your money is spent more efficiently. And then there are a variety of commercial customers that are just as secretive as various government customers. So, yeah. Cool. There's one who'd been up for a little while. Oh, sir? Right. So the full Humda data set, if we didn't have to rehydrate it 2 hours beforehand, it's like 1/3 of a billion, and it's 351, and we think we have about 50% headroom above that. So getting on to 500 million things, and each of these records has about 25 fields, 25 properties associated with it. So it's right close on 10 billion properties that we normally demo with, and so 15 billion maxing out that hardware. I mean, the cool thing about Moore's law is that there's a 50% sale every year and a half. So no, this is not custom hardware. This is like go to Dell.com and say I want a couple of servers. Yeah. Yeah. Cool. Other questions? Yeah.
We use Palantir Finance.
Yeah. Palantir Finance is pretty well specialized onto the time series data, and Dave Terrell can answer that much better than I can.
The
yeah.
short version is, it's a completely different set of problems because it's multiple dimensions. But it's a three-point challenge. So I work on the Palantir Finance product, which is basically a completely separate platform built on the same architectural guidelines, but not the same actual physical architecture. So we're actually currently solving a very similar problem to this for the finance world, but it's a completely different problem because it's n-dimensional. You've got time and object differences. So I don't have anything cool to show, but maybe next year.
He doesn't even have anything cool prepared, but he has lots of cool stuff that he produces.
After the Q&A, if people are interested in seeing more of this, we can move the party to, I think it's 1304, which is one of the classrooms in the foyer. We can hook up to a projector there and probably show you Palantir Finance if you want to come see that as well. We can pull up one of our demo rigs for that. But we should continue with the questions for now.
So a little bit, yeah. Some of the BD guys went a little bit crazy with it. They sort of just forked it and added a lot of UI enhancements that I would have liked to add if I had a little more time. Like you can do type ahead in here, filtering of that. There's this whole feature down here which we didn't show you. You can basically derive properties on the fly, like whatever amount plus. Oh, sorry, I've already forgotten the syntax. Amount plus income, and then this would make amount plus income. Right, and this was not in there at the time, but that's in there now. So they've added functions to this language to do things like talking about your outliers to eliminate things that are outside of certain parameters, and they've kind of gone nuts.
Yeah. Part of this presentation was how could we present something without getting too tied up on all the specific to customer kind of stuff. So there's a ton of it. Yeah.
Way in the back. Sorry about that.
Sorry. Yeah, the last question was what customizations went into the productized version of this besides the prototype that we saw. Sure. So this question is about how do we distribute data among the shards, and we tried the simplest approach, which is essentially hash the object ID, so pseudo-random distribution between shards, and then it turns out that's good. So if you drill down in any kind of subset like a geographic thing, you're not just pounding on one shard, you're pounding across all of them because they've all been hashed out across. Now. Why is it okay for things that are geographically close to each other to be spread between shards? Because they're dealt with independently as the separate view calls touch them on each shard, and they don't need to do any cross-shard communication.
This is that whole random access versus having to do a sequential read, right?
Yeah. Does that make sense? Cool. Anybody else? Who was up here first? Yeah, go ahead. Yes, yes. This is an in-memory store. Yeah. Yeah. Excellent question about what happens if a server goes down and how do you still have things going. Yeah, you have to replicate. This is something that we haven't built yet. So the real numbers on hardware outages are somewhere between 100 and 1,000 machines. You have outages frequently enough that it's a problem, and yeah, you have to deal with it at that point.
It's kind of worth mentioning. Somebody else's hackday project the year after this was to add replication to Horizon, and they got pretty far into it in just a week. So it's something that it sort of goes back to our customers administer these data centers, and they don't have Google-sized clusters at this point. So it's just not high enough on our radar to do, but there's no sort of technical barrier to doing it.
Yeah, so if a server goes down, you have to re-ingest, at least reload the indexes. I mean, this thing loaded from scratch. Everything that you saw here, we only started at 11:30. So, yeah, gives you some idea of how fast these things are. The next thing is, if you're worried about random hardware failures, this matters, but perhaps they're dominated by the frequency of other failures. Specifically, the whole cluster goes down, which doesn't really happen that often for Google quality administration, but definitely does happen. And if the whole cluster is going down, it doesn't matter whether you replicate it or not. You're just down.
One other note is that the most likely thing to fail on systems is a hard drive, which
yeah.
we're immune to. So
That's true. Not having to worry about hard drives is nice. Cool. Sir.
Are you looking at adding other visualization?
Are we looking at adding other visualizations? Yes, very much yes. Yeah, Dan, this is all you.
Sure. The thing is that the visualizations are pluggable in the actual product. So, whatever you can program, you can do, right? And I can't really go beyond that to say yes, you can do it.
Yeah. We have talked about all sorts of different kinds of things, and this is sort of a we don't have infinite time, so we've done what we think is the most valuable ones first, and take it from there. Yeah.
Once you drill down on a subset of data, is there any way to export that data to another tool?
Yeah. So once you drill down on a subset of data, is there any way to export it? Absolutely yes. This is again something in the productized version of this. We find that this ends up being really useful for people to make a first pass on the data, just triage it. What does this stuff even look like? And then I want to go do more fine-grained analysis on it. That's a really frequent use case.
Front row?
Yep.
About Palantir's business model, you get the impression that all sorts of government agencies are using Palantir government. So what's the future of Palantir government as more and more of the people who are available to use it have already adopted it? How is Palantir planning to make money on that in the future?
Should we give that one to Ari?
Yeah, this is a huge Ari one. Get ready for it.
So our business model is pretty simple. We build things of value and we sell them for money, right? But the interesting thing about the enterprise software market is that licenses have an expiration. So the way that our products tend to be licensed is that you license them for 2 years at whatever the list price is on a per core basis. In the second year, you pay a 20% maintenance fee, and then in the third year, you just buy it again. So what it looks like is about 60% of list price every year in perpetuity. So the answer is we just, and the other thing is that as customers add more users and they add more data, they buy more cores. And so as data sizes scale or use scales, they buy more licenses, and so that's how our revenue grows over time, as well as the government's a very big place, and you don't sort of sell to one place or another. You sell to each little island that has its own budget, its own data, and its own problems. And so we haven't even begun to penetrate the entire government by any means.
All right, so your licensing is
Per core.
Yeah, per core. It's the same thing that Oracle uses for pricing. So yeah. I wanted to say one other thing on top of that, which is that the Palantir government product is essentially a really good way of doing link analysis. Actually didn't show off too much of it today, but that example of campaign finance contributions and finding the linked things that nothing else really does, and there are a lot of applications of that inside and outside the government. So, yeah, we have a rosy future. Yeah.
How do you data change between production extraction or load to or do they have things if you have a very malformed database or you're running production you transform it into something that content does, if I update a record, will it propagate over?
Yeah, the question is essentially how do you manage data with a repository of record outside Palantir and pulling it into Palantir, and we have a lot of mechanisms for easily mapping these things that we talked about before, and then also just hey, look, it changed. I'm going to update that in Palantir as well. So yeah, we keep everything in sync, and it doesn't really demo that impressively because you're oh, hey, it just works, and that's kind of the point.
Back-end demo.
Yeah, it's a very back-end demo. Yeah.
Does things happen real time or is that just
The question is how fast do those things go? One that I worked on, the limiting factor was how fast were the disks that it was reading off of. In practice, it's always bound by how slow the other system is that we're pulling data. Yeah, it all depends on the exact hardware configuration, and usually the bottleneck is not us. Yeah, so we end up ingesting this stuff really quickly. And the next thing is, like people were asking about real-time stuff, and it was funny because it was a customer and a reporter from O'Reilly, and we were giving them this demo of Horizon, and the reporter from O'Reilly asked about real-time stuff, and this customer said, as far as we're concerned, like 90 days is really fast. And you're like, man, okay.
We could do that.
Yeah, no problem. So yeah, every night is like amazing to them. Yeah, and it's actually a lot faster than that. Yeah.
You mentioned that your licensing scheme is sort of per thread, and that a lot of the number crunching is actually done in parallel. Have you ever, has there been any thought towards leveraging like GPU solutions?
Sorry, what was the last part?
Has there ever been any thought inside of your company towards leveraging GPU solutions?
Oh, the question is about GPUs. We've considered it. The full question is, have we considered using GPUs to make this stuff faster? We've considered it. It doesn't make sense yet, but I mean that hardware is changing really quickly, and is something that definitely wouldn't have made sense 5 years ago. Doesn't really make sense yet, but could be really interesting to work on in the future. Michael Harris here has done a lot of GPU programming stuff, so yeah.
All right, well, people are starting to file out, so we'll just wrap it up. We'll be around if you want to come up and ask any questions or see any individual demos or anything like that. Thanks for coming.
Thank you very much.